Vado. Ok. Quindi inglese. Hello everyone. Hi. Welcome to this new meeting for Papers We Love. I think it's the first of the year. It's April, so we took our time. So if this is the first time you join us at Papers We Love, it's not really new meetup, but it's an interesting meetup. I think it's different from other meetups because we don't talk just about technology. We talk about papers and science. And so the idea is that we want to create a network of people and companies that want to share love for papers and computer science. So if this is your first time, you can keep in touch through our GitHub page, through our Twitter or X, whatever you want to call it. We are also on LinkedIn because God knows why you like LinkedIn. And then obviously we're on Eventbrite. And we also are on Discord, on the official Papers We Love Discord. So if you're interested, you can join us and we can hang there. There's a call for paper that you can use. You can use this link if you can propose a paper you wanna present. We're also trying to have this lightning talk session if you don't want to do a full 50, 40 minutes, 30 minutes talk. So you can do 20 minutes or less, and when we'll have enough of those, we're going to do a night with lightning talk. So if you're interested, if you're a first timer, you can try that. In general, this is the link for the call for presentation. And last but not least, I wanted to mention that next month there's going to be this conference called Software You Can Love. It's here in Milan, so you don't have to travel much. You can buy a ticket there. There's already a bunch of speakers. I think they have announced all the speakers, and there's different tiers for the tickets. You can attend the full 3 days, just 1 day, just the last day, blah, 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 blah. So I think it's cool, but the reason I wanted to mention this is also because on the first day, on the 14th, the night of the 14th, we're going to have a guest speaker. He's going to be King from Tiger Beetle DB. So it's going to talk about, I'm not sure yet, but it's going to be about distributed systems most likely. So if you're interested, stay tuned because we're going to publish soon the invite. And that's it. So let's give a round of applause for our speaker, and thank you.
So let's see if you will be uploading at the end of the talk. It's easy to upload before, harder to do it afterwards. So I guess you are all familiar with DALL-E and Midjourney. These are instances of diffusion models that are the technology that nowadays can enable us to transform text into images. And this technology has been very famous. Let me know if I should stand somewhere. Has become very famous for something like this.
Oh dear Lord, that's classic.
OK, I think we are done with the serious part of the talk. Now let's get started with something funny. Because this technology is also capable of stuff like this. This person does not exist. I know that it really does look real, but it does not exist. It was generated by Midjourney version 6, and it's the latest and probably the best at the moment diffusion model out there. Good. So we have seen a trivial application of the technology and a much more serious one before. You should notice that the pictures of the TikTok I showed before and this picture are about 12 months apart. And you already see a huge leap in the quality of the images. Right. But, I mean, we're not here to discuss TikToks. We are here to discuss science and technology. So what's behind these results? Well, like every serious talk, we should start from Wikipedia. And Wikipedia says diffusion models are a class of latent variable generative models. Very clear. A diffusion model consists of three major components: the forward process, the reverse process, and the sampling procedure. They learn the latent structure of a dataset by modeling how data points diffuse through the latent space. Well, my claim is that by the end of this talk, in 30 to 40 minutes time, you will know what each of these words mean. And you will have not a clear idea, but I hope an intuition of the basic principles behind the technology of diffusion models. You will not be able to build one, but I guess none of you will. But you will be able to know what happens when you type /image in Midjourney. Very well. Now, in order to understand how diffusion models work, we need to understand why they are called diffusion models. And to understand that, we need to take 2 or 3 steps back and go back to university or even to high school to talk a little bit about physics. Because, you know, diffusion models, the very idea of diffusion models comes from this paper. It's dated 2015. And it's titled Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. There is no mention about pictures. There is no mention about artificial intelligence, not in the title at least. There is a mention about unsupervised deep learning. It comes from the academia, not from the industry, which is kind of an outlier these days. It comes from Stanford and Berkeley. And it cites non-equilibrium thermodynamics. In the paper, there are a lot of mentions about physics, entropy, and so on. So to start, we will probably need to understand a little bit about entropy. What is entropy? Why is it important? What is the link with diffusion models and with generating pictures? Well, entropy is a basic concept in physics. It's a state variable of a system that measures how chaotic the system is. You can see entropy in action here, and by the way, you can also see diffusion in action here. At the very beginning of this video, you have 6 very distinct colors in a fluid. As time progresses, the colors mix between each other. So the amount of information in the system decreases because you don't have very specific points where the colors are. You don't have very specific information about the location of the colors. And entropy increases because the disorder of the system grows. Entropy is the protagonist of the second law of thermodynamics. And you basically know that in every isolated system, that is every physical system that does not exchange either matter or energy with the outside, every transformation goes towards an increase in entropy. It's like an irreversible law of nature, and someone links it to the very progress of time. You will say, wait a minute, but I can create order from chaos. I can go back. I can reverse entropy. I can create more ordered systems from more chaotic ones. It's what I do every time I build a castle on the beach. I take a bunch of sand, which is very chaotic, very disordered. There is no information there. And I make a very precise structure out of it. That's decreasing the entropy of the system. That's true, but the system of the sand is not isolated. It exchanges matter and energy with the outside. And specifically, you are providing energy to the system. It's the price you pay to go against these laws of nature. Fine. you would say, thank you for this reminder about high school physics. Why should we care? Bear with me for 5 more minutes, please. I need to open another parenthesis because I think it's very interesting, and I think it's the right audience to do so. Entropy as another interpretation. It's linked to statistics. So think about this. If you flip a coin 1 million times, a fair coin, you would expect to have about 50-50 between tails and crosses, heads and tails. Why is that? Well, it's not because of some strange law of statistics. It's just because it's much more likely to have this kind of combination. If you enumerate all the possible outcomes, you will see that there is only one outcome that is all tails, and there are a lot of combinations where heads and tails are 50-50. So the chaotic state, the one which has less information, is just more likely. There are just more states that lead towards chaos than towards order. It's also what you can see from this video. If you think that every particle of color moves randomly in the fluid, well, it's obvious to see how it is much more likely to end up in a state like this, where all the particles are mixed, than to end up in a state like the beginning one, where all the particles of the same color are concentrated in a specific point. It's not a matter of laws of physics, it's just a matter of statistics. It's more likely for particles to mix moving randomly than to stay in the same point. Very good. Now, let's move towards a more formal and structured representation. So we can see that there is a forward process where the information is destroyed, where the concentration of the color spreads uniformly in space. And we can imagine, we don't know if we can do it. I mean, we know that we can do it by providing energy to the system in a physical way. But there may be some way to reverse the laws of nature, to go against entropy, and to do the opposite. So from a state where the information is lower and where the color is spread uniformly across space, to go back and to recover the original state. Now you see where I'm going. Forward diffusion process, backward diffusion process. There is no idea of sampling procedure here, but we're getting there. Good. Still, we're talking about colors. We're not talking about pictures. What the hell? Good. But it's not very different. I mean, colors are just an example. You can think about the forward process, the one that goes towards an increase in the entropy of the system, as destroying the structure of something, going towards a probability distribution. Yeah, let's call it like this. A probability distribution that it's uniform and bears no information. If we think about pictures, pictures are made of pixels. How can we get a uniform distribution that bears no information? That's just white noise, right? If we have a picture made of pixels whose color are chosen at random with 0 average and a certain standard deviation, that's just white noise, and this is no information. So you don't know what's in the picture. It's just completely random. If we think about the pictures that we see on Unsplash, on the screensaver of our PC, they're exactly as the state where all the colors is concentrated. They are not random. They are very structured. They bear a lot of information. They have low entropy. So we can associate the beginning of the video about colors to real pictures, and we can associate the end of the video about colors with just white noise, random pixels. That's exactly what this paper says. You can interpret the structure in a picture exactly as the entropy in a physical process. Real pictures have low entropy because they represent very complex, very informative structures, the reality, while random noise has high entropy because it represents nothing. It bears no information. And exactly as in a physical system, it's very easy to go from a state where the entropy is low and the order is high towards a system where the entropy is high and the order is low. It's much more difficult to go the other way around. And in 25 minutes time, I will try to explain how to go the other way around. That is, to create order from chaos. That is the very title of this talk, or DOB-cow, order from chaos. Very good. Now, let's talk some math. We have discussed up until now in a very, let's say, abstract and not formal way. Let's try to formalize a little bit the ideas. So you go from some image to white noise. That's the forward diffusion process. How do you do that? Well, you can just generate random noise, right? You can go towards the last step in 0 step, exactly. You generate random noise from nothing, and that would be fine. No, it wouldn't, because then it would be basically impossible to go the other way around. So you need to destroy the structure in the image little by little, step by step. Why? We will see that. The roots are based in a paper published in 1949. Well, this kind of application was not even thinkable, let alone concrete. So what you do, instead of just generating random noise in the first place, is taking a real picture and adding some random noise little by little. Let's say 1,000 steps, 2,000, more or less. These are realistic numbers in model systems. So you have capital T equal to 1,000, and every step you add a little bit of noise so that the image is more and more similar to just white noise. But you have studied math, so you are smart about how you destroy the structure of the image. You do not just add noise at random, but you add a specific type of noise that has a Gaussian distribution. Why? Because think about the sequence. You add noise at each step. If at each step you add a Gaussian, then you know that the sum of any number of Gaussian distribution is again a Gaussian distribution. So if you know the average and the variance of the Gaussian distribution at each step, and you know them because you generate the noise, then you can go from step 0 to step small t in just one step, because you just add a Gaussian that is the sum of all the steps in between, right? That's engineering. That's the smart way of taking an easy procedure and make it efficient. So now you have an algorithm that is capital O of 1 to go from step 0 to every step from 0 to capital T. Very good. There are other subtleties in this formula, but I'll skip them for now, because I want to go to the hard step, going the other way around. So now you have white noise, and you want to recover a picture. For now, let's not attack the problem of getting a specific picture given a prompt. That's much harder, but we'll get to that in a moment. Let's say that we just want to generate one picture out of the whole probability distribution of all the possible real or realistic pictures. Very good. What do we need to know? We need to know the the function p theta of xt minus 1 given x of t. So what we need to know is the probability function of the transition from a step t to the step t minus 1. Right. What is this function? The problem is, for a generic process that destroys the structure of a picture, we just don't know. It's a generic probability distribution. It's very hard to reconstruct. But if the forward diffusion process is Markovian, that is, the transition function at each step does not depend on the history, but depends only on the last step. And if the noise that we add from one step to the other is Gaussian, and if this noise is very small, mathematically it tends to 0, but we don't care, we are engineers, we are just fine with very small, then the inverse probability function is also Gaussian. Great. Now we don't have to estimate a probability function, we just have to estimate a mean and the variance. Much easier. Kind of. Estimating the variance is hard. So what if we say that it's just the identity times a constant? I mean, it will work, right? There is no guarantee here. I mean, up until now, we are protected by mathematics. We are protected by theorems. Everything that I have said can be shown. I will not do that because it's very hard, and I didn't understand the proof altogether. But I mean, we trust the people that wrote those papers. The idea that an identity is good enough has never been proven, and is probably never going to be proven, but it works. So that's where engineers shine. Let's just try and see what happens. And what happens is that it works. Good. So now we are left with the average. We can estimate the average and then sample from a probability distribution, because we know the distribution itself, it's a Gaussian, and we know the variance. We have set it to a constant times the identity matrix. Very good. How can we estimate the average? It's still a hard problem, right? I mean, we have to estimate a vector that is the size of the number of pixels in the picture multiplied by the number of channels, so it's free, the free component colors, times the width of the picture times the height of the picture. It's still quite a difficult problem. We will see how engineers have tackled this problem in the future, but let's just say that in order to estimate a vector, what we can do is just to build a huge neural network and throw it against the problem and hope for the best. Yeah, that's what we did. That's the kind of neural networks that was proposed at the very beginning. We will see later the real structure of the deep learning model behind Stable Diffusion, because contrary to Midjourney and DALL-E, Stable Diffusion did publish a real paper with the details of their model, so we know how it's made. This was one of the first neural networks proposed to estimate this transition function in terms of the average vector that you need to go from one step to the next one. It's called a U network because of the architecture, and what you can see is that it starts with layers that are convolutional layers, the full size of the picture, and then shrinks the layers more and more, and then it goes up to the full resolution. You also have residual connections, then skip from high resolution to high resolution, and so on at each level. The idea here is that the smallest levels capture the semantic layer of the picture, while the high resolution levels are good at refining details, right? We will take this idea to the extreme with later architectures, right? So let's recap. We have a physical analogy. That is, we think that a picture is like a physical system. It can have low entropy and high information, a real picture, or high entropy, a low information, white noise. We can go from one state to the other. We can destroy information easily. We just add noise. And if we do it smart, we have very nice mathematical properties for the reverse process. If we destroy order in a smart way, we know that we can just estimate the average of the transition function of the probability distribution that goes from a more chaotic state to a more ordered state. How do we estimate this vector, this average vector? We do it with a neural network. Then the name of the game is just, once this neural network is trained, and we will see in a moment how it is trained, we just sample from each step to the previous one, taking the average of the Gaussian probability distribution, taking the variance that we know it's a constant time identity, and then sampling some samples from that probability distribution. Great. Now we have the forward diffusion process, the backward diffusion process. We have the sampling procedure because it's just drawing samples from a Gaussian. What we miss is, how do we train this stuff, right? Well, it turns out that it's pretty easy. Why? Because we have the forward diffusion process. It's us that destroy the structure in the image. It's us that go from order to chaos. So we are basically building ourselves the training dataset. We then start with a picture. We go to a step t wherever we want in constant time, because we have this nice procedure of the sum of Gaussian distributions. And then we say, OK, you go all the way back to step 0. And I'm building a loss function that compares the probability distribution of real pictures to the probability distribution that this guy generates. The more similar the distribution is, the better. So I know how to train with gradient descent this guy. If you do the math, it turns out that training this guy with a maximum likelihood is just untreatable, because you have to this here. This is parameterized because it's a deep learning network, so you have a finite number of parameters. But here you have a conditional probability distribution. So in order to go all the way back, you would have to condition at every step, and then you would have to integrate over all the possible small x of t. That is untreatable. So what you do is compute a lower bound and maximize the lower bound. That's doable because you get away the conditioning. Very good. And this is it. This is how diffusion models work. So you have the forward diffusion process from your left to your right. You're destroying structure. You're going from order to chaos. And then you have the backward diffusion process. From your right to your left, you're going from chaos to order. When you run Midjourney, and also the first version of DALL-E, then they hid this feature, you see that you launch the prompt, and what you see in the first steps is just a very, not a very neat picture. It's just something very obfuscated. Then it's get better and better and better. Yeah. Random noise and better and better and better. The problem is you still have to take each and every step in the backward diffusion process. You can skip steps in the forward one because you have this nice property of Gaussians. You can't in the backward one because you have the conditioning. And even if you train on the lower bound, in inference time, you cannot avoid conditioning. What the engineers did, bypassing a little bit of math, is like instead of doing 2,000 steps, which is impractical, doing like 20 by 20 or something like this. We don't know details of the limit journey, but we know that stable diffusion takes much fewer steps than all the ones that the theory would suggest. Very nice. Now, the theoretical part is over, at least for now. A little bit of heuristics. The first one is when you run the backward diffusion process, what you do is not really estimating this transition function, because it turns out is very difficult. Why? Because small x of t and small x of t minus 1 can be everywhere in the probability distribution of partially destroyed pictures, which is a very large space because of all the pixels that these pictures have. What you want to do is to compute the difference between x at step t minus 1 and x at step t. Why? Because again, from that paper by an English fellow written in 1949, you know that this probability distribution is Gaussian. Kind of. Similar to Gaussian, let's see. Similar enough to be considered Gaussian. And then what you do is you compute the noise that you would have added to go from step t minus 1 to step t, and you subtract it to the picture, right? In the forward diffusion process, you were adding noise. In the backward diffusion process, you are subtracting noise. Still, at every step, you are working on noise, not on the picture. The picture is just a byproduct. And we have already talked about the second heuristic, do it in small steps, because small steps actually the limit towards 0 is the condition that this guy needs in order to guarantee you that the probability distribution of the reverse diffusion process on the noise is a Gaussian distribution, which is much easier to estimate. 1949. Soviet Union had just detonated its first atomic bomb, right? No microprocessors, no internet, no GPUs, nothing. If someone tells you that base research is useless, well, tell them this story, right? Our model technology is based on things that were discovered when technology was not even thinkable, not even in science fiction. Very good. Now, the second to last actually, chapter of this talk. We have learned up until now how to create wonderful pictures from nothing but white noise, but we must understand now how to condition this process to generate the pictures we want. Because what Midjourney and DALL-E do is translating your textual prompt into a picture and not just generate a random picture. That's why they're so useful, and that's why you can build a video of the Pope in very nasty positions. Very good. What do you do? Well, a little bit of engineering first. I've lied to you, kind of, because the very first diffusion models were run onto full resolution pictures, but soon enough people realized there are just too many pixels. You don't need full HD pictures. What you want is to downscale the pictures, embed the pictures into spaces where vectors represent the semantics of the picture. So in order to say that a picture has a cat, you need a vector that is much smaller than a full HD picture. So what you do is you take a picture, you encode it in a much smaller space, then you run the forward diffusion process, you run the backward diffusion process, and then you have a decoder or upsampler, call it the way you want, right? That's great. That's just engineering. It doesn't change anything in terms of theory. It's just much easier to run training like this than like I explained before. And it also helps in inference time, because remember, every time you generate a picture, you have to run through the reverse diffusion process. Good. Then these guys from OpenAI, in this paper 2021, said, wait a minute, there is a very simple trick that we can use in order to guide diffusion. Let's assume that we have an unguided diffusion model, right? This gives a probability distribution on all the possible pictures. Now we do have, from like 2011, very good classifiers that can tell us, that can label pictures for us, that can tell us, look, in this picture there's a cat, in this picture there's a dog, in that picture there's a mountain. Very good. Now, let's think for a minute. What is the probability of a picture given a label? By a theorem. It's just the probability of the label given the picture times the probability of the picture divided by the probability of the label. Now, the probability of the label is just a normalization constant. We can take it away. The probability of the picture in itself can be drawn from an unguided diffusion model. Yeah, that's what we said for the last 20 minutes. And the probability of the label given the picture, well, that's just a classifier, right? As easy as it can seem. Probability of the picture given the label is the probability of the label given the picture times the probability of the picture divided by the probability of the label. If we take this away and we take the logarithm, this product becomes a sum. Then we take the gradient, and that's it. We have gradient descent for a classifier guided diffusion model. Genius. I mean, it's just genius. But it's nothing compares to what happened next. This is 2022, so classifier guided diffusion models had very little time to exist. Because in 2022, these guys from Google, I mean, consider this. This paper basically sets the foundation for all modern diffusion models. And they had just 2 papers from Google that wrote it. And they were writing a review paper to try and compare the performances of different classifiers for classifier-guided diffusion models. And what they found, by kind of chance at the very beginning, then they were very smart at formalizing why chance happened, was that the best classifier was no classifier, right? And then they changed the title of the paper, Classifier-Free Diffusion Guidance, and they had a huge success. How does this work? Well, the point is very simple. You do not train on unconditional probability of generating some picture. You train on conditional probability of creating some pictures. You just have to condition in a very special way for which you need the labels to be properly encoded as vectors, but the guy from OpenAI at the beginning of 2021 just published CLIP, which did exactly that. So these guys from Google took the bricks from OpenAI and put them together to get the classifier-free diffusion guidance. I was saying the idea is very simple. You train a classifier on conditional probabilities. So you don't use the probability of a generic picture X, but you use the probability of a generic picture X given the label encoded as a vector in the same metric space of the images. It's important. It's the same metric space. Then what you do is that at random, sometimes you train on the conditional probability, and sometimes you train on the unconditional probability. And the unconditional probability is just a conditional probability conditioned on a spatial token that means no text at all. Using this training procedure, you get DALL-E, basically. And then OpenAI made DALL-E. So this is the difference. In the classifier-guided diffusion, you have a diffusion model that takes as an input white noise, or better, a partially destroyed picture. It doesn't need to be white noise. It can be at each step from 0 to capital T. And then the iteration, because the model needs to know how many steps back it needs to perform. That's iterative. And then you have also classifier that are trained together using a common loss function. This gives guidance. I mean, the gradient of the classifier acts as guidance of the diffusion model, and then you recover a better picture. You do it for many steps, and you go to step 0. In classifier-free diffusion, you put the prompt and the iteration into the diffusion model, and you perform one step. These models are a little bit more difficult to build, much more easy to train. Because you don't have to train 2 models, you just have to train 1. And this is the real thing. So this is Stable Diffusion, not the latest version, because I didn't have time to update the slides. But you can see here many of the modules that we discussed during this talk. So you have a forward diffusion process that happens in latent space. This module there is the encoder, right? Then you have the backward diffusion process. You have this neural network that is the UNet. Of course, it's a Stable Diffusion is 2022, so you no longer have convolutional layers, but attention is all you need. You have transformers all the way from the beginning to the end, right? And you have conditioning that can come in many forms. I mean, you just need some vector in the same latent space where the picture in lower dimensionality lie. So you can have text, but you can also have other pictures. I mean, the in-painting works like this, right? You condition, you upsample, and then you get the picture back. Right, now it's really over. But before moving forward, I want to do a small exercise. I want to go back to this Wikipedia definition and see if we can explain each and every word. So diffusion models, right? The models that are based on the physical process of diffusion, like particles diffuse in a fluid, are a class of latent variable generative model. Generative, they produce picture. Latent variables, because the diffusion process happens in a hidden space. Latent from Latin means hidden, which has a lower dimensionality than the space of pictures. A diffusion model consists of 3 major components: forward process, reverse process, sampling procedure. We talked a lot about those. They learn the latent structure of a data set, that is, all the training process happens in the latent space, and they learn the structure because they learn to recreate order from chaos. By modeling how data points diffuse through the latent space, we already talked about that. Great. Spending half an hour to explain Wikipedia. 3 paragraphs. Good. Now, on to the limitation and merits of this technology. So the merits are pretty straightforward. Just look at this. I mean, this is a campaign from, I think, the beginning of 2023 by a very famous Italian company, Italian brand, actually. And it's already using generated pictures. You can tell this stuff is generated by Midjourney. Not everyone likes this campaign, as you can clearly see here. Boia che schifo di campagna. It happens, I mean, happens to everyone. But it's a trend that is very difficult to reverse. I mean, generating a picture like this is much, much easier than engaging an agency, creating a stage, hiring actors, and all the stuff like that. Much, much easier. And much cheaper as well. Then let's discuss a little bit some of the limitations of these models and how they can be overcome. This is a paper by OpenAI. It's DALL-E 3 technical report. Look at the difference between these pictures and these pictures. I mean, especially from the first column, paying for a quarter-size pizza with a pizza-size quarter. No, not really. I mean, I will not read these, it's much longer, but this picture is much better, and look at the face of this guy. What's happening here is, again, a very smart move by the guys at OpenAI. They said, we have DALL-E, not the best diffusion model, great, but we do have GPT 3.5, which is by far the best large language model. So what if we improve the prompts that our stupid user give us, and we feed our not great diffusion model with the output of our great large language model? So what DALL-E 3 does is, before starting the reverse diffusion process, let's go to GPT a little bit, and let's ask him, improve this prompt, please. That's prompt augmentation. OpenAI never disclosed how they do it, what prompt do they give to GPT. Nowadays, they're using GPT-4, of course. But they do disclose that on a benchmark of human evaluators, the augmented prompts, the pictures generated with augmented prompts, perform much, much better than the raw pictures. As far as we know, Midjourney does not use this trick. And if you want to use it on Stable Diffusion, you have to do it yourself, right? Same paper by OpenAI. I'm copying and pasting from the paper. So this prompt augmentation works, but it has dark side. During testing, we noticed that this capability is unreliable, as words are missing or extra characters. I inverted 2 slides, sorry, I need this one first. Our synthetic captions are prone to hallucinating important details about an image. For example, given a botanical drawing of a flower, the captioner will often hallucinate a plant genus and species and put it in the caption. DALL-E 3 is unreliable at generating imagery for specific terms. So the point is that the prompt augmentation has the same issues of large language models. So for very specific subjects, like specific types of plants, they tend to invent. Most likely, since the time this paper came out, a month ago, they have fixed this kind of problem somehow. At least they have mitigated it, but still it's something we should take into consideration. And this is also very interesting. So diffusion models are notoriously incapable of generating text and hands, right? Why? For text, there is a very neat explanation that comes from this OpenAI paper that says, look, prompts are embedded, right? They are vectors in a vector space, and the atoms of embedding are tokens. So how can a diffusion model know what a letter is, right? They don't know. They don't know about our lexicon. They don't know about our alphabet. So how can they be capable of generating text, specific words, specific sequences of letters? They shouldn't, and they weren't. Then Midjourney 6 kind of solved this issue. We don't know how. And what about hands? Well, hands are tricky just because what is a hand, really? I mean, they appear in picture in so many different ways. They are always in a different place. I mean, I can't really keep my hands still. I could keep moving them. And so it's very hard for a diffusion model that learns by examples to reconstruct exactly how many fingers in a hand, because if I keep it like this, you will see 4. If I keep it like this, you will see 3 probably, and so on. So we kind of know how the guy solved this problem. That was taking a lot of pictures of hands and training the model specifically on that data set. I mean, fine-tuning the model specifically on the data set. OK. Now I'm really done. And I want to leave you with one last story. In September 2023, in the US, there was a fierce debate about generative AI coming for knowledge workers. And Fiverr, that is a very well-known platform for selling services, freelancer services, said, look, this is a great marketing opportunity. We can stand for the guys on which we make healthy margins. So what we're going to do is to put in every major US town manifests like this one. AI took my job, the job of Gabby, a freelance AI copywriter. AI took my job to the next level. The message is pretty clear. AI is not coming from our jobs, it's not coming for our jobs, it's coming to make our jobs much more productive. I'm Emanuele Fabiani, and the head of AI at Extreme, where we build AI solutions for scale-up and corporates. If you're curious about us, feel free to follow our LinkedIn page or to go and talk with the 3 guys in the last row. And with me, of course. I also love going around speaking at events, conferences, and so on. I don't get the chance often to have a very technical talk like this one, so I enjoyed a lot this night. I will come back if you want with more questions and more papers. So please feel free to give me any feedback you have, because I really like to go around talking. So any suggestion you can provide me with to improve how I deliver this talk is very welcome. And now I will not stand for much more between you and the pizzas and the drinks and whatever, and that's it.
Are there any questions for the speaker?
Yeah. Yeah, we need the microphone.
Hello. Thank you, first of all. Still trying to wrap my head around the whole thing. But so at a certain point, you did show how an image gets noised until it gets destroyed. So the word destroyed is accurate because it is a destructive process at the end of the day. And then you show how it gets denoised. So that, especially like in Midjourney, where you can actually see that happening, it doesn't happen the same way it gets noised, because you don't see just dots disappearing. You see like rough shapes, and then you see the shapes taking some meaning into that. Is that because the noising and the denoising is actually happening in the latent space? So actually the noising and the denoising is not happening at all in what we see. There are no dots on any image. What is happening on a meaning, on a semantic space, in some feels like it's a semantic space.
Yes,
and
exactly.
So at that point, the thing that actually generates the image is nothing that we talked about today.
Yeah.
The encoder,
kind
the
of.
decoder, let's call it.
If we go here, so at each, OK, first point, Midjourney shows you only some checkpoints in the denoising process, not all of them, because they don't want to send too many pictures from their servers and your client, and so they optimize this step. But what really makes the difference is that what you see is here in the pixel space, while the reverse diffusion process happens here in the latent space, that it's much smaller. So once you convert this, so let's say that there is white noise here, so you are at the very beginning of the denoising process. You do one step of denoising, you get here, let's say you do many, and then you get to a checkpoint. You have this decoder that basically flattens the noise, so you don't get white noise here, but you get this smooth and soft picture that you can see in the image here.
Okay, so my question is the D of the decoder. What is that thing?
What?
The decoder itself. What is it?
It's again a neural network.
Oh,
So
it's another neural network.
yeah.
Okay.
It's another.
Okay.
Yeah, I mean, this is like a U network, and this stuff is trained to go from the output of this network to the pictures themselves. So 1, 2, 3 neural networks.
Okay, so the one, like the encoder and decoder are two neural networks we
Yeah.
didn't get into today much because they are less of a refined object and it's more of a standard neural network. That's the thing.
Yeah, I mean, think about autoencoders. So autoencoders are neural networks that go from a high-dimensional space to a latent space, then back to a high-dimensional space, right? These stuff, this guy and this guy, are two pieces of an autoencoder. So they're pretty, I mean, I would not say standard because we can do a whole talk about those, but they are another module in the book of deep learning.
Okay.
Are they trained separately from the diffusion process? Like the encoder and the decoder?
That's a good question. I don't know. I don't know the answer.
You mean from a different thing?
Or maybe from the image to
I'm
the
not-
transformed image? Or like if you use techniques from the autoencoder category?
I'm not sure, honestly, because so what you have here. Well, actually, you could. Okay, the starting point is that I don't know the answer for sure. I haven't read it. So thinking about it, I would say that this Z and this Z, if this diffusion model works, are very similar to each other. So these two guys can be thought as the two parts of an autoencoder that you can train on ImageNet without anything else. While here, you need the diffusion process in between. So if I was to try now to build a model like this, I would probably train them separately. But I'm not sure if there is any problem with this approach.
Don't you need the? Let's see. Sorry. Wouldn't you need the prompt to allow the encoder to transform an image into a latent space? Because the image itself contains information, but it contains no meaning. Usually, you use the prompt to give a meaning to go into a representation of the image.
That's not accurate, I think, because the conditioning happens in the UNet in the reverse diffusion process.
That in creating an image. I'm thinking when you are creating the encoder is transforming an image in a pixel space into a representation space.
Mm-hmm.
How do you define, how do you train, how do you get the representation space elements so that you can actually train it to transform into that?
I think you don't, because once you have once you have the latent representation of the image.
But how do you get to that?
Autoencoder. So what you do is you go from a high resolution image to a latent space back to a high resolution image. So what you're doing is basically compressing the image into a lower dimensional vector.
Okay, lower dimensional, I can imagine. You can use anything analytical or whatever. But if the latency space is a representation of a semantic space, that means that there has to be some extra information attached to the image so that you can actually map it into something semantic. And that could be the prompt. So you can have images and prompts so that you create your points in the latent space. Otherwise, you're just using an arbitrary transformation, which will not work in the other way around, because the other thing that the other network, the cool one, has works in the representation space thanks to the prompts. Or not?
Maybe not. I mean,
Okay.
let's go a little bit outside of the scope of this talk, but it's just too interesting not to do it. I happen to have here, because I was reading it today. Okay, so this is the paper from Clip. That is the way you embed pictures and text in the same space. So what you do here is completely independent from a diffusion process. So what you do here is you have text, you have images, and what you do is you train embeddings of text and images so that the okay, so sorry, let's get a step back. The dataset is pairs of text and images, right? So the pairs are built by just scraping the internet for the pairs, so you know that they're good, and probably breaking some license, but that's not a problem. What you do is you maximize the cosine similarity between the couples, and you minimize the cosine similarity between the wrong couples. So you can do this is irrespective of a diffusion process. So I think that once you go here, you can train these guys outside of the loop, and you can train this guy in another process.
So you're going to have a couple of image and text to train the encoder and decoder pairs.
Yeah,
Yeah, that
but completely separate from the diffusion model.
But it's going to be you still are going to need prompts and images to train the encoder. That was my question. Okay.
Yeah.
Sorry. Okay.
Okay.
That was actually what I wanted to ask.
Are there any other questions? No.
What do you think are the limits for the future of this architecture, and how it can be improved apart from more power? Exactly.
My question is, how much more do you want to improve from this? I mean, it's already great, and I think that
It can be improved a lot.
yeah, it can be improved a lot, but I mean,
If people can recognize that it's made by an AI, it can still be improved.
yeah, possibly, but I mean, I'm not sure if there will be in the near future, let's say, breakthroughs like classifier-free diffusion guidance or classifier-guided diffusion. I mean,
Attention.
sorry?
Attention versus transformers.
Yeah, I mean, this is already applied here. And I mean, other breakthroughs like this, I don't think they're likely to come from these applications. Right now, the frontier here is small marginal improvements on this kind of processes and pushing them towards videos. That's very hard. It's not a theoretical problem, it's an engineering problem. Because videos are made of 60 of this stuff for each second, so they're much harder to process, and they have a temporal sequence. Temporal sequences are very painful because you need to keep consistency over time, and that's what even Sora is struggling with. So what I think the improvements will be marginal improvements on this kind of stuff. Possibly taking some innovation from the field of large language models to these kind of models, like architectures like Mamba or something like this can be in the future applied also to this context, and then solving the engineering problems preventing us to generate videos at this moment. That's it. I don't think there will be much more. What I think it's not there yet in terms of applications of this technology is user experience. I mean, yesterday OpenAI released a feature to change a specific part of an image with a prompt. So what can be really improved, in my opinion, is having easier ways to access this technology. I mean, people don't want to use Photoshop. People want to use ChatGPT and generate wonderful pictures and maybe generate 10 pictures with the same face and maybe put their face on a picture and so on. So this kind of interaction is probably what tech giants will focus on in the near future, plus what we mentioned before. But I'm curious about your opinion. Do you think there will be something groundbreaking in this world?
I'm not an expert, to be honest, but yeah, I mean, we have assisted to changes in architecture in the last years that completely changed the landscape. That was not just more GPU, let's say.
Mm-hmm.
So
it's possible. I mean, we shall see in a
like,
few months' time.
Like transformers, as you said, as an issue with the memory usage, the context and stuff like that. So maybe that's something that can generate videos I don't know, of like 1 minute, for example, something like that.
Mm.
All right, let's thank again our speaker, and thanks to Daniele who found the speaker actually, and he's helping with the organization. Thanks to Matteo, who's often, almost always helping us with recording and bringing his own equipment. It's been wonderful. So, and thanks to you for coming. So, thank you.